Hey everyone, welcome to today's Explainer. We're diving into a topic that quite literally shapes the physical and digital world around us. We're talking about the geometry behind shape changes. Whether you're looking at how a video game renders a moving character, or maybe how an architect manipulates spaces on a blueprint, what you're actually witnessing is the geometry of motion. Now, I want to start things off with a fundamental question. Just think about this for a second. If a shape moves, does it become a new shape? I know, it kind of sounds like a philosophical riddle, right? But in geometry, this is exactly what we call the invariance arc. As we manipulate objects today, we're basically going to act as geometric detectives. We'll be looking really closely at what actually changes and what stubbornly stays exactly the same. Okay, let's dive into this. Here's our roadmap for today. First, the rules of shape changes. Second, sliding, flipping, and turning. Third, resizing shapes, also known as the enlargement. Fourth, when transformations combine. And finally, number 5, avoiding common geometry mistakes. Now, believe it or not, every single geometric movement you're going to encounter in GCSE and IGCSE curriculums boils down to just this number, 4. There are exactly 4 main transformations that govern all of these movements. Just 4 fundamental ways to manipulate our shapes on a grid. So let's look at the ground rules. Section 1, the rules of shape changes. So, a transformation is exactly this. It changes the position, size, or orientation of a shape without changing its essential properties. As we go through the 4 transformations today, I really want you to keep a mental rule of 3 scorecard. We're going to judge every single move by how it affects 3 things: size, shape, and orientation. Those are our core metrics. Keep them in mind. Moving right along to Section 2. Sliding, flipping, and turning. All right, first up is translation. The action word you absolutely need to lock into your memory here is slide. A translation simply slides a shape from one position to another. The shape, the size, the orientation, all completely unchanged. The lengths and angles, yep, unchanged too. We communicate the slide using what's called vector notation. It basically looks like a tall bracket with 2 numbers stacked on top of each other. The top number tells you exactly how far to move horizontally. So positive is to the right, and negative is to the left. The bottom number? Well, that tells you the vertical movement. Positive is up, negative is down. So if you have a vector of 4 over -2, that means you slide the shape 4 units right and 2 units down. It's simple, it's precise, and it's completely rigid. Next up, we have reflection. Now, the action word here is flip. A reflection literally flips a shape across a mirror line, which is also known as the line of reflection. Now, this could be a vertical line, a horizontal line, or even a diagonal one. But listen, there's a golden rule here. Every single point of your shape must be an equal distance from that mirror line, and it has to be exactly perpendicular to it. So if a point on your triangle is, say, 3 squares away from the mirror line, its reflection must be exactly 3 squares away on the direct opposite side. Now, what's really interesting here is when we compare these side by side on our scorecard, a pretty fascinating difference emerges. Both translation and reflection keep the shape and size completely unchanged. But while translation keeps the orientation exactly the same, a reflection completely reverses it, creating a literal mirror image. It's an absolutely crucial distinction to remember. Okay, our third rigid changer is rotation. The action word for this one is turn. A rotation turns a shape around a fixed point. Just think of pinning a piece of paper to a corkboard with a single thumbtack and then spinning it. That fixed point, that thumbtack, is called the center of rotation. And no matter how far you spin the shape, the distance from any point on that shape to the center always remains perfectly constant. But to perfectly execute a rotation, you can't just say turn it. You always need 3 specific pieces of information. First, you need that center of rotation, basically the coordinates where the thumbtack goes. Second, you need the angle, like how far are we actually turning it? Usually this is going to be 90, 180, or 270 degrees. And third, you need the direction. Are we going clockwise or anti-clockwise? If you miss even one of these 3, your transformation is incomplete. And again, back to our scorecard, size and shape remain unchanged, but orientation absolutely changes based on your turn. All right, on to Section 3, resizing shapes, also known as the enlargement. So this is our 4th and final transformation, enlargement. The action word here is resize. An enlargement changes the physical size of a shape, but, and this is super important, it keeps the exact same proportions. The shape remains mathematically similar. The internal angles, they don't change at all. but the side lengths change proportionally based on what we call a scale factor. You actually find this by taking the new length of the image and dividing it by the original length of the object. And this brilliantly illustrates how a scale factor is just so much more than a simple multiplier for growth. I mean, if the scale factor is greater than 1, like, say, 3, the shape obviously becomes larger, 3 times the side lengths. But if the scale factor is a fraction between 0 and 1, like a half, the shape actually gets smaller. It's still called an enlargement mathematically, which, trips a lot of people up, but it is actually a reduction in size. Now here is the really mind-bending one, a negative scale factor. If your scale factor is -2, the shape doesn't just double in size, but it gets projected entirely to the opposite side of your center of enlargement, completely inverted. Honestly, it's like it passed through a portal. Section 4, when transformations combine. Now, when you're asked to combine transformations, say you need to translate a triangle and then immediately reflect it, the golden rule is sequence. Step 1, apply the first given transformation to the original shape. Step 2, apply the second transformation to that new, freshly moved image. Order is absolutely critical here. Seriously, if you swap the sequence, you will almost always end up with a completely different final image in a completely different location on the grid. Never, ever mix the order. Okay, here's the grand payoff for our invariance arc, bringing that rule of 3 scorecard to life. Translation? No changes to size, shape, or orientation. It's pure, rigid sliding. Reflection? Size and shape stay exactly the same, but orientation is perfectly reversed. Rotation? Size and shape remain identical, but orientation changes based on the turn. And enlargement? Well, this is the only one where size actually changes. The shape remains similar, meaning proportions and angles stay intact. But the orientation might change if you're dealing with those tricky negative scale factors we just talked about. Honestly, take a mental snapshot of this. It's your ultimate geometry cheat sheet. And finally, Section 5, avoiding common geometry mistakes. Let's rapid fire through these common pitfalls so you never make them. First off, mixing up clockwise and anti-clockwise rotations. Always double-check your direction. Second, reversing the translation vector. Remember, the top number is horizontal, left or right, and the bottom number is vertical, up or down. Don't swap them. Third, forgetting that reflections actually reverse orientation. If your reflected shape is facing the exact same way, well, you just translated it, you didn't reflect it. And finally, confusing negative scale factors with reflections. Yes, a negative scale factor flips the shape to the other side of the center, but it scales it too. It's not just a simple mirror reflection. So, the crucial point is this. When you're staring down a complex geometry problem, just cut through the mathematical jargon and anchor yourself to these 4 undeniable actions. Translation equals slide. Reflection equals flip. Rotation equals turn. And enlargement equals resize. If you can attach the technical terms to these simple, unforgettable action words, you'll immediately know exactly how to manipulate the space in front of you. I want to leave you with a fascinating, slightly provocative thought to wrap up our explainer today. Imagine you rotate a shape, and then you translate it. But then you realize you could have achieved that exact same final position and orientation with just one perfectly placed reflection. So if 2 combined transformations create the exact same shape on the grid as a single different transformation, which one is the true movement? It really just goes to show how deeply interconnected the invisible mechanics of geometric reality actually are. There is always more than one way to move through space. Thanks so much for focusing in with me today, and keep exploring the geometry all around you.